Welcome to the Explainer. Today, we are unlocking a feature that can absolutely transform the way your equipment runs. We're going to master the internal PID functionality of the Schneider Electric ATV320 variable frequency drive. And look, whether you're a complete beginner who's never even touched a VFD, or you're a seasoned automation engineer looking to really dial in your parameters, this Explainer is built specifically for you. We're going to take this incredibly powerful built-in capability and break it all down, step by step, so you can use it to make your system smarter, smoother, and vastly more efficient.
Okay, let's dive right into this. Here's our roadmap for today. First, the magic of PID control. Then, we'll hit the key ATV320 PID parameters. Third, a step-by-step setup guide. Fourth, an awesome case study on a booster pump. And finally, number 5, the biggest takeaways and common mistakes you definitely want to avoid. All right, Section 1, the magic of PID control. Let's understand the absolute basics. So what is PID anyway? Well, at its core, PID control is simply a continuous feedback loop. It looks at exactly where you are, compares it to where you want to be, calculates the difference, which, by the way, we call the error, and then it applies a correction. It does this using 3 very distinct mathematical terms: proportional, integral, and derivative. And the ultimate goal of all this math? Absolute system stability. Now, I know those acronyms can feel a bit like alphabet soup, so let's picture filling a giant water tank up to a very specific line. The proportional action, that's basically how wide you open the valve based on how empty the tank is. If it's totally empty, you crank it all the way open. But as the water gets closer and closer to the line, you proportionally close that valve. But what if you have a tiny leak and the water just never quite reaches your target line? That is exactly where integral comes in. It looks at how long you've been sitting just below the target and literally forces the valve open a little wider to push it right over the finish line. Finally, derivative is kind of like your anticipation. It sees the water rushing up fast and closes the valve slightly early so you don't splash right over the edge. To really get why this is such a game changer, just look at the stark contrast between the old way of doing things and using the VFD's internal PID. A system without PID is, well, it's basically blind. It's just banging on and off at full speed. Think of an air compressor that runs at 100% until it hits max pressure, violently shuts off, and then turns back on the second pressure drops. That wastes a massive amount of energy, and it absolutely tears apart your mechanical components. But by using the VFD-based PID, the drive modulates the motor speed smoothly and precisely. As demand drops, the motor slows down seamlessly. And the best part? Because the ATV320 has this built right into its own logic, you can completely eliminate the need for expensive external PLC hardware. Moving right along to Section 2, key ATV320 PID parameters. Let's get into the actual terminology. Okay, engineers, this is for you. Inside the drive, our 3 water tank concepts translate to these exact parameter codes. RPG is your PID proportional gain. That ranges from 0.01 to 100, and it has a factory setting of 1. Next, RIG is your integral gain, which also defaults to 1, and then RDG is your derivative gain. Now notice something here. The factory setting for derivative is exactly 0. In most standard industrial motor applications, like pumps and fans, proportional and integral are really all you need. Derivative can actually introduce some nasty instability if your sensor signal is noisy, so the drive smartly keeps it safely off by default. So the crucial step here is knowing how to physically find these settings. When you power up the ATV320, you're going to use the jog dial right on the graphic display terminal to navigate the main menu. You'll drop into the drive menu, then hit Configuration, then Full, and finally, you'll land in the Application Functions menu. Having a mental map of this is so important. This exact screen is your gateway to turning your drive from just a basic motor starter into a highly intelligent process controller. Now, before we even think about tuning those gains, we have to scale our system using a few core process parameters. First step is PIF, which stands for PID Enable, that literally just turns the function on. Next is FBK, your feedback input, which tells the drive exactly where to listen for your sensor. And finally, PIP1 and PIP2. These are your minimum and maximum PID process parameters. They establish the absolute operational boundaries for whatever process you are trying to control. Think about it. If you don't tell the drive what 0 looks like and what maximum capacity looks like, the math in the PID loop has absolutely no context and it simply won't work. All right, Section 3, Step-by-Step Setup Guide. It's time to actually configure the loop. Listen up, because there are some very strict initial steps you must follow before you even touch the proportional tuning. Step 1. Switch the drive into PID mode using that PIF parameter. Step 2, and honestly, this is a massive pro tip, right out of the manual. You need to set the deceleration ramp adaptation parameter, code BRA, to no. You absolutely have to stop the drive's built-in auto-adapting ramp logic from fighting with your brand new PID logic. Step 3. Set your PID ramp, PRP, to the minimum time allowed, without causing an overbraking fault, of course. And step 4, dial your integral gain, RIG, all the way down to its minimum, and verify your derivative, RDG, is sitting at 0. We want to isolate the proportional gain entirely first. Okay, now we tune. You actually want to shock the system a bit by switching the drive on and off, or by rapidly changing the target reference. While you're doing this, you adjust your proportional gain, RPG. Your goal here is a very specific compromise. You're looking for a fast response time, which usually results in a slight overshoot of your target, followed by just 1 or 2 brief oscillations before it perfectly settles. Once you've nailed that quick but stable response, you can gradually increase your integral gain, RIG, to really dial in that steady-state pinpoint precision. But remember, you've got to move slowly. Pushing these gains up too high, too fast, that's going to cause violent mechanical instability, and nobody wants that.
And this graph brilliantly illustrates why those scaling parameters are so incredibly vital. What we're looking at is an analog 4 to 20 milliamp sensor being mapped to an actual physical volume of 6 to 15 cubic meters. The PIF parameters on the bottom axis represent the raw electrical feedback coming straight from your sensor. The PIP parameters on the vertical axis represent your actual real-world process range. If you map these correctly, your internal references and presets are going to align flawlessly with the real-world physics of your tank, your pipe, or your ventilation duct.
Let's bring this into the real world. Section 4, Case Study, Booster Pump.
Picture this. A facility has a standard constant pressure booster pump set, and its job is to keep the water lines pressurized. But using a standard starter, it's just running blind. Every single time someone opens a valve, the pressure drops, the pump kicks on at 100%, violently slams the pipes with maximum pressure, and then shuts right back off. This creates massive pressure fluctuations, incredible mechanical wear and tear, and it burns through an absurd amount of electricity during those night shifts when demand is virtually zero. It's a nightmare. Enter the ATV320. By retrofitting the system with a drive, the internal PID completely eliminates those pressure spikes. As valves open and close all over the facility, the motor seamlessly speeds up and slows down just enough to hold the pressure line perfectly flat. But it gets better. The drive utilizes parameters SLE and SLU. Those are your sleep and wake thresholds. This introduces a true sleep mode. If demand drops to 0, the drive safely puts the pump to sleep, completely eliminating wasted energy, and then it automatically wakes it back up the exact millisecond the pressure drops again. So we achieved perfect pressure, we eliminated external PLC hardware, and we delivered massive energy savings.
And that brings us to our final stop, Section 5, Takeaways and Common Mistakes.
Let's rapid-fire the absolute must-know takeaways here. Number 1, always start your tuning with your integral gain at an absolute minimum and move it up slowly. 2, leverage this feature. The internal PID saves you serious money by eliminating the need for external hardware controllers. 3, your math has got to be right. The PIP and PIF scaling parameters must map perfectly to your sensor's physical limits. And lastly, whatever you do, don't forget to turn off the auto-adapting deceleration ramp, BRA, so the drive doesn't fight your own loop.
Now, I need you to hear this. Here is the single most common and honestly most dangerous mistake you can make. Do not ever enable the PID loop without first configuring your FBK feedback source. For example, making sure your pressure transducer is actually wired properly and assigned to analog input too. If you turn on PID and the drive has no sensor telling it what is going on, the math just goes completely crazy. The drive will start hunting uncontrollably, ramping the motor up to max speed and dropping it back to 0 violently, over and over again. This will destroy your mechanical equipment. Always ensure your feedback is reading correctly before you hit run. So we've covered the theory, the parameters, the exact setup, and the pitfalls. The ATV320 is an incredibly capable piece of machinery that, frankly, often sits totally underutilized in cabinets all over the world. So I'm going to leave you with this question to think about. What standard, clunky, horribly inefficient on-off applications in your own plant could be revolutionized today by simply activating the ATV320's internal PID? Take a walk around your facility, take a hard look at your pumps and your fans, and think about the amazing optimization opportunities that are waiting right in front of you. Thanks so much for joining me on this explainer, and I will catch you on the next one.